Good afternoon. So I'm going to present my work on hydrogen molecular ions and the Dirac equation. So the hydrogen molecular ions, they're simple quantum systems. They're made out of three bodies, so one electron and two nuclei. And the energy levels and other properties are calculable with high accuracy because of the simplicity. So here there is the energy curve as a function of the internuclear distance. And this is the 1s sigma ground state curve for the electron, and these are real vibrational transitions. So these ultra narrow real vibrational transitions can be measured with high accuracy with ultra cold trapped ions. And because we can both calculate them and measure them with high accuracy, then these molecules are promising tests for fundamental theories and also determination of fundamental constants, such as the ratio of mass of the proton to the mass of the electron. So regarding the accuracy of these transition frequencies, here, this is the relative uncertainty of these frequencies as a function of the year in which they were either calculated or measured. In black, you can see that the accuracy for the theory has been steadily increasing over the past few years, but the accuracy of the experiments has simply surged over the past couple of years. So now that the experiments are more accurate than the theory, we have to improve the theory. And to know how to do that, we have to know that the theoretical value is given by a sum of several contributions. So these are all the contributions for this real vibrational transition frequency. The first of them is the solution of the Schrödinger equation as a three-body problem, which gives this contribution. And then we have relativistic and relativistic recoil contributions. Here the numbers in red are the uncertainties. And we can calculate these contributions either as a three-body problem or in the Oppenheimer approximation. I'm going to make a small digression to talk about it. So these calculations, they rely on the three-body solution for the Schrödinger equation, which means that all of the three bodies are allowed to move with respect to each other. But for smaller corrections, we use the Born-Oppenheimer approximation, which means that we fixed R, the internuclear distance, and we solve for the motion of the electron in the Coulomb field created by the nuclei. And this is justified because the masses of the nuclei are much larger than the mass of the electron. And so for the Dirac equation, we're going to adopt the Born-Oppenheimer approximation. So continuing with the contributions for the transition frequency, then we have all of these quantum electrodynamic contributions. And I would like to highlight this one, the one loop self-energy, because it's the largest source of uncertainty of the theory. And then we also have nuclear finite size and polarizability contributions. And when we adapt all of these contributions, we get a relative uncertainty of 7.6 times 10 to the minus 12. So as I said, the one loop self-energy, it's the largest source of uncertainty for the theory. It's represented by this Feynman diagram. This means that an electron with momentum P emits and then reabsorbs a photon. And so far, this quantity has been calculated using an expansion in powers of V over C. But our goal is to do a full relativistic calculation of this quantity. And if we manage to work it out with a 7 to 8 digit precision, then getting back to our contributions, these two uncertainties will be negligible with respect to the other uncertainties. And this is going to lower the whole uncertainty by a factor of about 2. So this is the formula we have to evaluate to get the value of the one loop self-energy. And I would like to highlight this. This is the Dirac wave function. And also this mathematical object is the Dirac green function. And as we need these two mathematical objects, then it means that to get this quantity, we need first a high precision solution of the Dirac equation. So this is the Dirac equation. Here, psi, it's a 4-component object. It's the Dirac wave function. We split it into 2 components, phi and chi. Phi are the large components and chi are the small components, because in a weakly relativistic system, phi is much larger than chi. So here beta and alpha are the 4x4 Dirac matrices. And also V here is the Coulomb potential. And for the hydrogen molecular ions, we take Z1 equals Z2 equals 1. So yeah, here E is the energy and C is the speed of light, P is the momentum. So to solve the Dirac equation, we're going to use an iterative method, which was proposed by Kutzelnig in 1989. So the first step of this method is to solve the Schrödinger equation. And we're going to take the non-relativistic energy and wave functions of the Schrödinger equation as the initial approximation for the relativistic energy and wave function of the Dirac equation. So after we've solved the Dirac equation, we're going to update the energy. So the iterative method gives us a formula to do that. And then we're going to update the large components phi, and then we're going to update the small components chi. And then we're going to iterate over these 3 steps until convergence. Convergence in that sense means that if we do one more iteration, then the change in energy is smaller than a certain threshold, which has to be small. So some advantages of this iterative method. So with respect to perturbation theory to perturbative solution for the Dirac equation. So there are no expansions based on a small parameter. It's much easier to automatize, and it should also converge faster. And also regarding the variational method, then it avoids the problems linked to the variational method, namely the variational collapse. So to solve the Dirac equation, we have to put some conditions on the basis functions. So we're going to choose some families of functions f and g to expand the large and small components phi and chi. So here A1, A2, B1 and B2 are the coefficients of the expansions, which we're going to solve for. And we have then the kinetic balance condition, which means that the basis function for the small components chi has to be given, has to be given by the basis function for the big components with the application of sigma p on it. Sigma here is the Pauli matrices.
But this is an approximate condition.
This is a condition on the basis function.
Yes, but it's an approximate condition. It's not exact.
Yes, no. I don't know what to say, sorry. So this is important to guarantee the non-relativistic limits of our Dirac solution. So here I'm going to present the basis set that we're going to use. We're going to use the exponential basis set, which was proposed by Kurabov for the Schrödinger equation. So here R1 and R2 are the distances from the nuclei to the electron. And big R here is the internuclear distance, which is fixed because we're doing the Born-Oppenheimer approximation. And here alpha I and beta I are parameters that we choose randomly. So some advantages of this basis set. It allows the matrix elements to be calculated analytically, which is very important for the accuracy. It allows extremely accurate solutions for the Schrödinger equation. So we got E0, the energy for the Schrödinger equation, which is our initial guess, accurate to more than 30 digits, and also better represents the behavior of the wave function near the nuclei, contrary with respect to the more commonly used Gaussians. So I'm talking about, this is the Schrödinger wave function, actually. I'm talking about these 2 cusps that exist on the nuclei and that are well represented by the exponential basis functions. And it also gives the right behavior at long distances. So some numerical details, we coded it using Fortran 90. We did it with octuple or 12-uple precision. So just to compare, double precision means that the computer stores floating point numbers with 16 digits. Octuple precision means 64 digits. And we used 12-uple precision just to control for the accuracy of the octuple precision. So the largest basis functions that we used had 498 components, and this is for each of the 4 components of the Dirac equation. So here it's, this is actually one of the results. This is the energy calculated for the Dirac equation as a function of the basis size. We subtracted the energy extrapolated to infinity basis size. And you can see that as the basis size increases, our energy converges to a certain value. So finally, some more clear results. So we calculated the energy for internuclear distance of 2 atomic units. The energy is also in atomic units. So this is our result. This result by Cooley and Colby was the most accurate result available when we started doing this work. And with respect to this result, we improved the accuracy by about 7 orders of magnitude. Recently, this result by Cooley and Schiller came up, and it agrees perfectly with our result up to the 20th decimal place. So just to clarify, this is a curve I showed you in the beginning. We calculated the energy for an internuclear distance of 2. If we wanted, we could run this method for several values of R and then do a full relativistic version of this curve. So some cross checks, because when we got this, our result, this result by Cooley and Schiller wasn't available. So to make sure it was correct, we used perturbation theory. We used perturbation theory to expand the energy and wave functions of the Dirac equation. We used the formalism proposed by Rutkowski and Kutzelnig in the 80s. And we calculated the first 3 corrections for the energy. So this is our value for the U1, the coefficient proportional to C to the minus 2. So you can see that these were the results available in the literature, and we managed to improve the accuracy by several orders of magnitude. And the same for the E2 coefficient, and also for the E3 coefficient, we also improved the accuracy. So when we adapt all the calculated orders in perturbation theory, we get a very good agreement between our result using perturbation theory and our result using the iterative method. So as you can see, the difference between them is only about 10 to the minus 19, which is comparable with the expected order of magnitude of the non-evaluated 4th order correction that we don't have. And finally, we just implemented another way to solve the Dirac equation. We used the modified Dirac equation, which was proposed by Dial in 1994. So it's the Dirac equation that takes into account the kinetic balance. So to do this, we expand operators in a basis set, and we solve a generalized eigenvalue problem. So here, A and B are the coefficients of the expansion of the wave function that we're going to solve for. And each one of these elements of these matrices are themselves matrices. So these are blocks of matrices. And some advantages of this, another way to solve the Dirac equation, which we call the direct method, is that it gives us the whole spectrum of the Dirac equation. And it also agrees with our results obtained using the iterative method. And it also gives us the Dirac green function, which is going to be necessary to evaluate the one loop self-energy. So some final remarks. We improved the accuracy by 7 orders of magnitude with respect to the work that was available when we started doing this work. And this is largely due to the use of the exponential basis function. So the iterative method allows us to obtain the wave function for one state at a time, but we just implemented this alternative method by solving the Dirac equation directly, and it gives us the whole spectrum. So the next step will be the calculation of the one loop self-energy correction. But we're still working to improve the precision even further, and we are investigating approaches other than the restricted kinetic balance and also trying other basis functions. So this is my team from LKB in Paris. Jean-Philippe Carr is my supervisor, and we collaborated with Vladimir Korobov. So thank you very much.
Thank you. Did you check with the hydrogenic wave function?
With what, sorry?
With this atomic hydrogen wave function. Because atomic hydrogen wave function doesn't satisfy this kinetic balance condition. So if the kinetic balance condition is not satisfied for the hydrogen atom, why it is satisfied for H2+?
I think it's satisfied for the hydrogen atom. It's the non-relativistic limit of the Dirac equation, so it has to be satisfied.
Relativistic wave function,
yes.
The kinetic balance condition is not satisfied. Exactly. It's an approximated relation. If it is approximated relation, how come it is an exact relation for H2+?
We don't claim.
Sorry, you presented the result with 30 digits. You don't claim these digits are significant for the solution of Dirac equation? That's complete.
Okay.
So
conditions on the basis functions,
then
not wave functions.
Okay, that is a condition for the basis,
yes.
not for the wave function itself. Wow, this makes a difference. This makes a difference.
We calculate all of these coefficients. I think you thought that we calculated just those coefficients and then used it to get these. We calculated A1, A2, U1, B2.
Yes, but that means now I understand because it was just one small explanation. Then, Gordon.
Yeah, I just wanted to comment. You may be aware that I have an alternative method of constructing the basis functions where the large and small components are completely independent, independent variational parameters, and you still avoid variational collapse, provided you have the same number of degrees of freedom for both the large and the small component. And it works perfectly well. I've demonstrated that it satisfies relativistic sum rules, and it's a perfectly valid way of doing it. You don't need kinetic balance.
So we did run this. We did use the third. Actually, we used this direct method, but without considering the kinetic balance, and we get a result that is less accurate than this one. We get only 17 digits instead of 20 digits.
You should now program yourself and prove that you can do it better. This will be an answer.
So it works. There is no variational collapse, but it's less accurate.
Who else? Oh, please, Paul.
A few years ago, we did the calculation in Cassini coordinates with the Dirac equation for the two centers because we wanted to see what happens if you have like a collision of uranium on uranium. Did you try to go up in Z to see what happens and compare to Cassini coordinates is a way to make a two center in a simple way. It's like in astrophysics.
You mean if we did these calculations for higher Z?
Yes.
Yes, we did also using this method, and we got results that agree with the literature. Not as accurate as not 20 digits, but we did with Z equals 50. I don't remember how many digits we got, but it agreed with the values in the literature.
At the time we had done uranium and thorium, I think. So it would be nice to compare.
Further questions? Yes, Grzegorz?
Yes, thank you very nice talk. So at the beginning, you show us this table with all the possible contributions, and among these, there were like the nuclear finite size and polarizabilities.
Yeah.
But these were quoted without uncertainties. Can I ask why is that?
Because it doesn't, these uncertainties are much more important. It doesn't.
No, this is not the right answer.
It-
At this 4-digit precision, the terms, if they use the recent muonic deuterium results, then it is below. Yes,
Okay.
because your determinant is so accurate, then it is below this. Yes, if they use the muonic values, then the uncertainty, at least for the finite size, for polarizability, the term polarizability is also marketed. Then so this is means if they use most recent term polarizability, this is the right number. It might be the right number without uncertainty.
Okay, thanks.
So let me comment that you presented the formula for the self-energy, which is incorrect. So maybe it's a good starting point.
Where's
For the electron self-energy, okay, this is not a complete formula, just something approximate starters. And then I'm not sure if you can use this kinetic balance condition to represent the Dirac propagator. It is known that people have done this calculation for hydrogen very accurately. Vladimir Yerokhin, who was a speaker, he was doing this such a calculation very accurately. So as far as I know, for the calculation of self-energy, one cannot use kinetic balance condition for the propagator, and also the formula should be corrected. It has to include the complete expression.
Thanks.